In this video, we will explain the multiple voltage rails and power sequence requirement of the MTK car infotainment system board, and how to accomplish this via a special multi-rail PMIC sequencer IC. We'll show how to change the functionality by reprogramming the MTP memory and check the power sequence during cold cranking.
Hello everyone! In this video I will explain the design of the multiple voltage rails and power sequence of this MediaTek car infotainment evaluation board.
Many devices on the MT2712 board need specific voltages. The MT2712 SoC itself already needs at least 8 different voltage rails, and the rest of the devices also need their supplies. Let's have a look at 4 of the MT712 SoC voltage rails: the 1.0 core rail, the 1.05 BCPU and LCPU rails, the 2.15 AVDD and the 1.8 VIO voltages. You can see that when I switch on the board, these voltages start in a specific order. This power sequence is needed to ensure the correct startup of the SoC. For the MT2712 board, there are totally 8 power rail sequences, which all can be accomplished by the RTQ5115, an I2C controllable 12-channel power converter sequencer PMIC. It includes 4 buck converters and 8 LDOs, and has an integrated MTP non-volatile memory that allows multiple times programming of many functions. The voltage rails can be enabled via I2C, external enable pins, via the power button or automatic startup from input voltage. The voltage rails and sequence of the MT2712 SoC are generated as following. Sequence 1 is the core rail, which is generated by an RTQ2134 high current PMIC and enabled by LDO6. Sequence 2 are the BCPU and LCPU rails, which are generated by another RTQ2134 PMIC and enabled by LDO7. Sequence 3 is the 2.15 AVDD, which is generated by LDO1. Sequence 4 is the 1.8 VIO, which is generated by buck1. In the same sequence, the 1.05 AVDD is generated by a separate LDO, RTQ2516, and this LDO is enabled by buck1. Sequence 5 is the 3.3 VIO, which is generated via buck4. Sequence 6 is the 1.1 volt DDR voltage for the MT2712 DDR rail and the external DDR memory, which is generated via a fast RTQ2103A ACOT buck converter, and this is enabled by LDO5. Sequence 7 is the 3.3 volt SD card interface supply, which is generated by LDO8. Sequence 8 is the system 1.2 volt, which is generated by buck2. Buck2 also enables the LDO that powers the MT6630 connectivity chip. As you can see, the RTQ5115 can be used for both supply voltage generation and power sequence. Let's have a look at the RTQ5115 EVB and its interface. The Richtech RAN board is used to control the RTQ5115 I2C bus via the PC. The MTP memory in this IC on the EVB was already programmed for the MT2712 board. I will measure LDO6, LDO7, LDO1 and buck1, which are the first 4 signal rails in the power sequence. The RTQ5115 in the MT2712 EVB is programmed to start up via the power button. So when I apply 5 volt and press the power button, you can see that LDO6, LDO7, LDO1 and buck1 indeed start in the correct order. When I press the power key for 4 seconds, the power board will switch off, and as you can see, the power sequence is now the reverse of the power up sequence, which is also the requirement for the MT2712 SoC. For the power off sequence enable signals, it is important that the falling edge goes to 0 quickly. This is accomplished by enabling the ground discharge function of the LDOs. Now let's run the RTQ5115 GUI. As the RTQ5115 has many programming features, the GUI has several pages for setting different register values. The first page is for sending specific register commands. The second page lets you change specific register values. The third page lets you save or load a complete MTP memory content. Map 1 page shows the buck enable-disable, the buck voltage and slew rate, LDO enable-disable, LDO voltages, and LDO ground discharge on-off control. Map 2 shows the PMIC startup and shutdown configuration. Map 3 shows the power button and startup shutdown power sequence method. Map 4 shows the interrupt configuration, and Map 5 lets you set the power sequence of each channel and write the MTP memory. As you can see, the power sequence indeed follows LDO6, LDO7, LDO1, buck 1, etc. as is needed for the MT2712 SoC. For the MT2712 evaluation board, the power sequence is activated by pressing the power button. But in the final automotive application, the MT2712 power-up sequence should be started when the battery voltage is applied to the board. Let's reprogram the MTP memory to accomplish this. First, we remove the power, then we set the MTP write projection pin jumper from low to high. Now we can switch on the power and press the power button. We can now change the RTQ5115 from power button startup sequence into VIN enabled startup sequence by changing the register setting of the VIN low V sequence enable from low to high. We can also program the exact input voltage level where the power down sequence will start. I will change the default 3.1 volt value to 3.5 volt and then click Write. The startup input voltage level will be 400 millivolts higher, so will become 3.9 volt. Now we need to update the MTP memory in map 5, so I set the MTP page 1 and MTP page 2 to write and then click Write. The new values are now written into the MTP memory. After removing power, I set the MTP protection jumper back to low. When I now slowly increase the input voltage, you can see that the startup power sequence indeed starts at 3.9 volt, and when lowering the input voltage, the shutdown sequence starts at 3.5 volt. Let's check how this system behaves during cold cranking. I apply the Arduino cold cranking generator to the 5 volt preconverter and connect this to the RTQ5115 EVB. I will measure the RTQ5115 EVB input, the first two signals of the power sequence LDO6 and LDO7, and the last signal of the power sequence, which is buck 2. After I enable the cold crank generator and slowly increase the voltage modulation, you can see the 5 volt rail starting to drop. As long as the input voltage dip stays above 3.5 volt, the RTQ5115 will keep normal operation. You can see that as soon as the input voltage drops below 3.5 volt, the RTQ5115 will start the power down sequence, and it will complete the full power down sequence even if the input voltage has already recovered. After the power down sequence is finished and the VIN is above 3.5 volt, the RTQ5115 will initiate the correct startup sequence again. This behavior will ensure that the MT2712 SoC system board will always shut down and start up in the correct manner, also during cold cranking.
I hope you now have a better understanding about electronic power design for automotive applications. Please stay tuned for more interesting videos at RichTech, your power partner.